I want to speak directly to you, the listener, for a second. Think about the physical world around you right now.
Yeah, literally anything around you.
Right. The device you are listening to, the chair you are sitting on, the air in the room. If you try to push any physical object, it pushes back.
It resists you.
Exactly. It physically resists you. We call that resistant inertia, and we tie it to this concept called mass. And if you have ever taken a physics class, you were probably handed a textbook that treated mass as just this, fundamental passive property of matter.
Like a bowling ball just inherently has more this passive mass thing than a tennis ball.
Right. It just sits there. It resists being pushed. It generates gravity. And that is just the end of the story. It is treated as an axiomatic noun, basically a static label on a box.
Which is how we've always looked at it.
But what if everything you were taught about mass and inertia in those classical physics frameworks is, well, what if it's fundamentally incomplete? What if mass isn't a passive thing at all?
This is where it gets crazy.
Yeah. What if, instead of being a noun, mass is actually a verb? Like an active, continuous, furious, electrodynamic action happening at the quantum level every single microsecond of your existence.
What's fascinating here is why this matters to you, the person listening right now, and really how deeply this upends our foundational understanding of reality.
Oh, totally.
Standard physics, the physics used to engineer bridges, launch orbital satellites, teach university-level mechanics. It treats mass as an axiomatic scalar.
Which basically means what in plain English?
In plain English, that means it's just a number that exists without any underlying physical mechanism to explain why it exists. It's just a mathematical assumption. We plug the number into Newton's equations, and it works beautifully for macroscopic engineering.
Right. F equals ma.
Exactly. But it leaves a massive philosophical and physical black box at the center of the universe.
And that black box is what we're prying open today.
We are. We're moving from a 19th century model of reality, where particles are just viewed as hard little classical spheres possessing unexplained mass, into a 21st century model of a deeply interconnected quantum superfluid vacuum.
And the goal of today's deep dive is to trace that exact journey. We're going to explore what is known in the source material as the Redefined Mass framework.
It's an incredible body of work.
It really is. It's this revolutionary physical model that was first seeded in 2006 and has been relentlessly perfected, debated, and just mathematically battle-tested over 2 decades.
We've got a formidable stack of sources to guide us through this, too.
Yeah, highly technical manuscripts, advanced physics preprints, theoretical books that detail the entire evolution of this framework. But what makes this so compelling isn't just the sheer elegance of the math.
It's the human element, the debate.
Right. It is the story of a transcontinental intellectual debate between 2 brilliant physicists. On one side, we have Pavel Vrbovsky doing this foundational, pioneering theoretical work in Banjski Petrovac, Serbia, starting back in 2006.
And on the other side, stepping in years later to solve the literal universe-breaking paradoxes that Vrbovsky's early work created, we have Pavel Banić in Michigan, USA.
It's such a wild intellectual collision.
It really is. This transcontinental collaboration is essentially the story of classical intuition colliding with quantum reality. Vrbovsky provided the conceptual spark, the realization that inertia isn't just a given, but a consequence of electromagnetism.
But his tools were older.
Right. His initial tools were purely classical. It took Banić's deep expertise in nonlinear quantum field theory and thermodynamics to actually make the model survive the extreme stress tests of relativistic physics.
Right, let's unpack this from the very beginning. We need to start at the bedrock of Vrbovsky's 2006 vision in Serbia.
The origin of inertia.
Yes, which becomes postulate I of this new framework. So as we just established, standard classical mechanics defines inertia axiomatically. It just is. You try to push a boulder, it's hard to push. Why?
Because it has mass.
Right. And why does it have mass?
Because it does.
Exactly. It's an entirely circular logic loop. And Vrbovsky looked at that circular reasoning and basically decided it was scientifically unacceptable.
He said, no, we can do better.
Yeah. He proposed that inertia has an explicit electrodynamic origin.
He completely refused to accept the black box approach to mass. To understand the alternative he built, we really have to look intimately at how charged particles behave when they move through space.
Because classical mechanics usually ignores the electrical charge when calculating basic kinematics, right?
Exactly. Vrbovsky made the charge the central protagonist of the whole story.
Let me try to put this into a real-world analogy for everyone listening, and then we can scale it down. If you go to the grocery store and you try to push a heavily loaded shopping cart from a dead stop, It pushes back against you.
It physically resists your attempt to accelerate it.
Right. In the old classical model, we just wave our hands and say the card has a lot of mass, so it resists acceleration.
Yeah.
But let's apply Vrbovsky's concept to a single charged subatomic particle, like a quark or an electron.
Okay, let's zoom in.
Why does that microscopic particle push back when you apply a force to accelerate it? Because it's not just sitting there being heavy.
No, it's not. The particle pushes back because of the fundamental laws of electromagnetism. Specifically, it relates to the implications of Maxwell's displacement current.
Let's visualize this for the listener.
Sure. When a charged particle is sitting completely stationary relative to an observer, it has a static electric field radiating outward from it. But the moment you apply a force and try to accelerate that charge, you force it to move through space.
And moving a charge does something very specific.
Yes. One of the most unbreakable rules of electromagnetism is that moving an electrical charge generates a magnetic field.
So you are essentially forcing the universe to spin up a magnetic bubble around the particle as it starts to move.
That is the exact mechanism. But, the universe does not give you that magnetic field for free.
Energy has to be conserved.
Exactly. Building and maintaining that co-moving magnetic field requires work. The particle must expend energy to establish it. So, as you push the particle, the system is simultaneously siphoning off some of that applied kinetic energy to build its magnetic field.
Creating a back reaction.
Right, a self-inductive back reaction. The physical resistance you feel when you push the particle. The literal resistance to building that localized magnetic bubble in the vacuum of Vrbovsky proved mathematically that this electrodynamic resistance is what we experience macroscopically as physical inertia.
That reframing completely changes how you view the physical world. I mean, when I push something, the resistance isn't just inert dead weight.
No, it's the universe actively demanding energy to spin up a magnetic field.
That is so cool. And Vrbovsky didn't just propose this as a neat philosophical thought experiment, did he?
Not at all. He actually derived the rigorous math for it.
Right, giving us what the sources call the virtual mass equation.
Yeah, he proved that the virtual mass of a particle, which is denoted as m sub v, isn't some abstract scalar number pulled out of thin air. It is a very specific, calculable electrodynamic state.
And that derivation traces directly back to Maxwell's equations, right?
Exactly. He took the energy density of the self-generated magnetic field and equated it to the classical kinetic energy of the particle.
Now, I know looking at physics equations in an audio format can be tough to visualize, but this one is incredibly elegant and it's essential to the whole framework.
Yeah.
We really need to break it down.
It's beautifully concise. It's m sub v equals mu naught times q squared, all divided by 6 pi times a sub 0.
Okay, let's translate those symbols into physical reality for the listener.
Let's do it. The mass of the particle, the m sub v, is directly proportional to the square of the particle's electrical charge.
That is the q squared in the numerator.
Right. And the mu naught is just the magnetic permeability of the vacuum, which is a constant. So fundamentally, the more electrical charge a particle has, the stronger the magnetic field it generates when it moves.
And therefore, the more mass it inherently possesses.
Exactly. But the critical part of the equation is the denominator. Mass is inversely proportional to the particle's physical radius, denoted as a sub 0.
Meaning, if the radius in the particle shrinks, the denominator gets smaller.
Which means the calculated mass goes up.
Okay, so that mathematically makes perfect sense.
And profoundly physically, too, because if you shrink the radius of the particle, you are packing that self-generated magnetic field into a much tighter, denser spatial volume.
The energy density just skyrockets.
It does. And the grand implication of Vrbovsky's equation is that kinetic energy isn't just some abstract, invisible mathematical property floating somewhere in the vicinity of a moving body.
It's physical.
It is physically, literally localized within the magnetic fields generated by the moving quarks and electrons. When you give a particle momentum, you are physically storing real energy in its surrounding magnetic field.
Okay, I follow the logic, and it's brilliant. But I have to push back here, because there is a glaring, immediate problem with this theory.
I think I know where you're going with this.
Yeah, if you're telling me that mass explicitly requires an electrical charge to generate this magnetic field, what happens when we look at neutral particles?
Ah, the neutron problem.
Right, take the neutron. It is famously neutral. It has a net charge of exactly 0. It doesn't interact with electromagnetic fields in the same way a proton or an electron does.
True.
So if I take a net charge of 0 and plug it into Vrbovsky's equation for Q, 0 squared is 0. According to this straightforward classical formula, a neutron shouldn't be able to generate a co-moving magnetic field,
Which means it shouldn't have any electrodynamic inertia.
which means it shouldn't have any mass. But neutrons clearly have mass. I mean, they account for roughly half the weight of the observable matter in the universe.
You're highlighting the exact critique that would completely dismantle the theory if left unaddressed. It's the first major hurdle any unified theory of mass absolutely must clear.
So how do you get around it?
Vrbovsky anticipated this, and he resolved it by developing what he called the absolute charge model. He recognized that looking at the neutron as a fundamental, featureless sphere of zero charge is a macro-level illusion.
We have to zoom in. We have to actually look inside the neutron.
Exactly. We have to look at the quantum chromodynamics, the internal structure. A neutron is not a single point. It's a composite particle. It is made of three smaller fundamental particles called quarks.
Right.
Specifically, it contains one up quark and two down quarks.
And those quarks carry fractional electrical charges, right? They aren't whole integers like an electron.
Correct. They carry very specific fractional charges. The up quark has a positive charge of 2/3, and each of the two down quarks has a negative charge of 1/3.
Okay, so if you're an observer standing far away from the neutron, you add those charges together. Plus 2/3 minus 1/3 minus 1/3, that equals exactly 0.
That's why the macroscopic outside world perceives the neutron as electrically neutral. But Vrbovsky realized that the virtual mass equation, the actual mechanism of generating a magnetic field, does not care about the distant observer's perception of a canceled net charge.
Because internally, those quarks aren't just sitting still.
Not at all. They are moving furiously. They possess immense kinetic energy. And when those three quarks are physically moving within the boundary of the neutron, each individual quark is a moving electrical charge.
Therefore, each individual quark is furiously generating its own localized magnetic field inside the particle.
Exactly. The energy required to build and maintain those internal magnetic fields is still being demanded by the universe.
So the magnetic fields don't just magically vanish or cancel out into nothingness internally just because the electric charges add up to 0 externally.
Right. The vectors of the fields might overlap and interact, but the energy density required to source them is additive.
Okay, so how did he calculate it without losing his mind?
To calculate the virtual mass of a neutron without having to do maddeningly complex dynamic quantum internal field calculations for every microsecond of quark movement, Vrbovsky devised a brilliant statistical simplification.
Which was?
He summed the absolute values of these constituent internal charges.
Oh, by absolute values you mean stripping away the positive and negative signs, treating all charge as just a magnitude of electrodynamic action.
Exactly. The absolute value of plus 2/3 is 2/3. The absolute value of minus 1/3 is 1/3. You take the three quarks and add their absolute magnitudes together.
So 2/3 plus 1/3 plus 1/3 equals 4/3.
Yes. Therefore, in Vrbovsky's absolute charge model, the neutron is assigned an effective absolute surface charge of 4/3 e.
Wow.
Even though it is completely net neutral to the rest of the universe, its internal moving quarks are generating a massive localized magnetic field, giving the neutron its substantial virtual mass.
That is an incredibly elegant bridge. I mean, it connects the macroscopic observation of a neutral particle with the microscopic, chaotic, electrodynamic reality of its internal components.
It really was a stroke of genius.
So Vrbovsky lays this incredible bedrock in 2006. It makes sense. It derives mass directly from classical electromagnetism, and it completely solves the neutron problem.
But
We are explicitly calling this deep dive a 20-year intellectual journey for a reason. Because as beautiful and intuitive as Vrbovsky's classical model was, it harbored some fatal theoretical flaws.
very fatal.
It started to severely crack when physicists tried to push it to extreme limits.
The transition from brilliant intuition to established physics is usually where theories die. You see, Vrbovsky relied entirely on 19th century classical physics. Maxwell's equations, basic 3D geometry, continuous fields.
And what happens when you push those?
Well, when you try to apply classical continuous rules to extreme relativistic scenarios, like a particle accelerating close to the speed of light, the mathematics and the physical geometry simply break down.
The sources detail three major breaking points of this classical model, right?
They do.
Let's explore the first breaking point, which the sources call the relativistic compression requirement.
This one is tricky.
Standard Einsteinian relativity tells us that as an object accelerates and approaches the speed of light, its relativistic mass increases.
Yeah.
As velocity goes to c-lat, mass approaches infinity. So if mass is an electrodynamic phenomenon, how did Vrbovsky mathematically explain this relativistic mass increase?
We have to look back at the virtual mass equation we just discussed. M sub v equals mu naught q squared over 6 pi, a sub-zero. Remember the inverse relationship. Mass is inversely proportional to radius.
Right.
The charge of the particle, the q, doesn't change just because it's moving faster. The permeability of the vacuum, mu naught, is a constant. So the only variable left to manipulate in that classical equation is the radius, a sub-zero.
So to explain why mass increases as a particle accelerates toward the speed of light, Vrbovsky fundamentally required the particle to physically shrink in volumetric size.
Yeah.
If the radius gets smaller, the denominator shrinks, and the overall mass gets bigger. Okay, mathematically, that checks out perfectly with his equation. But mathematics is just the map. What is the physical territory? What is the physical mechanism actually forcing a solid particle to shrink just because it's moving fast?
The mechanism is the co-moving magnetic field itself. As the particle accelerates, that self-generated magnetic field gets exponentially stronger. And according to classical electrodynamics, a strong magnetic field exerts a physical pressure.
Like pushing in on it.
Yes. Vrbovsky theorized that this magnetic field generates a crushing inward pressure on the boundary of the particle. The faster the particle travels, the stronger the magnetic field becomes. The harder the inward magnetic pressure squeezes, the smaller the particle's radius gets. And therefore, by his equation, the higher its mass becomes.
I could visualize that. It's like diving deeper into the ocean, the pressure increases, and if you take a balloon down with you, it compresses.
That's a good way to look at it.
But here is where we hit the first massive universe-breaking paradox. The sources call this the internal permeability paradox, or more bluntly, the faster-than-light problem.
The FTL problem, yeah.
I'm going to introduce an analogy to explain the physical dilemma here for you listening. Imagine you have a spherical water balloon, and you want to squeeze it perfectly inward, compressing it into a smaller sphere. But you can't touch it with your hands. You have to use sound waves from all directions to create the inward pressure.
Okay, cracking.
For that water balloon to actually shrink uniformly, the material inside the balloon has to be highly compressible. It has to be physically receptive to letting that external pressure push its boundary inward. If the inside is incompressible, the balloon just pops or deforms. It doesn't shrink.
That analogy translates perfectly to the electrodynamics of the particle. For the vacuum space inside the boundary of the subatomic particle to actively allow this inward magnetic squeeze, its internal relative magnetic permeability, which physicists denote mathematically as μ sub R2, must drop to a value of less than 1.
Okay, let's define that real quick. Permeability is essentially a measure of how much resistance a material offers against the formation of a magnetic field.
Right.
If mu sub R2 is exactly 1, that is standard empty space. It offers baseline resistance. So if mu sub R2 has to be less than 1, it means the interior of the particle has to become a highly diamagnetic medium.
Yes, it has to actively allow the magnetic pressure to compress it by offering less resistance than the standard vacuum.
Okay, so that is the physical requirement for the compression to occur. Now, mathematically, stating that mu sub R2 is less than 1 seems innocuous enough. You just write the inequality on a chalkboard.
It seems harmless.
Right. But physically, within a purely classical framework, it drops an absolute bombshell on the laws of physics. Because classical physics strictly dictates how the speed of light, specifically the phase velocity of electromagnetic waves, behaves when it travels inside any medium.
Let's look at the equation for that phase velocity, because this is where the classical model completely falls apart. The phase velocity, denoted as v subphase, is equal to the speed of light in a true vacuum, which is c, divided by the square root of the medium's electric permittivity times its magnetic permeability.
So the equation is v subphase equals c over the square root of epsilon sub R2 times mu sub R2.
Exact.
So if we plug Vrbovsky's requirements into that equation, we have a massive problem. Let's assume the internal relative electric permittivity, the epsilon, remains at the normal vacuum baseline of 1. But the permeability, the mu sub R2, absolutely must be less than 1 to allow for the magnetic compression we just talked about.
Right.
That means you are multiplying 1 by a fraction less than 1. So the entire number at the bottom of that fraction inside the square root is less than 1.
You're hitting on the core paradox right there. When you take the speed of light, c, and you divide it by a number that is less than 1, the resulting number gets larger than c.
Oh, man.
Yeah, which means the phase velocity of electromagnetic waves inside the compressed particle must physically exceed the speed of light. Mathematically, v sub phase is greater than c.
You've just broken the universe. You cannot travel faster than light.
You've broken the foundational causality of Einstein's special relativity. If information, or in this case, the phase of an electromagnetic wave, propagates faster than the speed of light, you destroy causality.
Effects can literally precede their causes.
Exactly. You introduce retrocausality into the particle's internal dynamics. It is a fatal theoretical consequence.
Wow.
Vrbovsky's model absolutely required the particle to shrink to explain relativistic mass increase, which fundamentally required an internal permeability of less than 1, which classically and unavoidably required faster than light travel inside the particle.
It was a theoretical dead end. Paradox.
A huge one.
And it is so frustrating because the initial premise of electrodynamic inertia makes so much sense. But it wasn't just the speed of light that broke. There was a second fatal flaw the sources outline, and this one was purely geometric. The asymmetric equatorial boundary collapse.
This geometric flaw is slightly easier to visualize, but it is just as devastating mathematically as the faster-than-light paradox.
How so?
Well, Vrbovsky built his model by assuming particles like quarks and electrons were perfect, 3D spherical charge shells. Think of them as tiny, perfect, hollow basketballs of charge.
But the magnetic fields generated by a moving object aren't perfectly spherical. We see this with the Earth. The Earth generates a magnetic field, but it doesn't form a perfect uniform sphere around the planet. The field lines emerge from the poles and wrap around the equator.
Right. The geometry of moving charges dictates that the magnetic fields are azimuthal. They wrap tightly around the equator of the moving particle relative to its line of motion. But crucially, the magnetic field strength drops all the way to 0 at the exact front and back poles of the particle along the axis of movement.
So if this co-moving magnetic field is supposed to be the mechanism providing the inward pressure to compress the particle, the pressure isn't symmetrical.
It's highly destructively asymmetric. As the particle accelerates and approaches the speed of light, this crushing inward magnetic pressure is squeezing the absolute life out of the particle's equator.
But simultaneously,
there is absolutely 0 magnetic pressure pushing inward at the front and back poles.
it's like wrapping a heavy-duty ratchet strap around the middle of a delicate glass balloon and cranking it as tight as you can while leaving the top and bottom completely unsupported. The perfect 3D spherical geometry completely breaks down.
It violently deforms. Under that extreme asymmetric relativistic pressure, the classical 3D sphere flattens and collapses into a 1D string-like structure.
A 1D string.
Yeah, Vrbovsky's assumption of a rigid, classical 3D spherical shell was simply too simplistic to survive the reality of relativistic speeds. The structure literally destroys itself under its own self-generated asymmetric field pressure.
So we have faster-than-light paradoxes shattering causality. We have 3D particles crushing themselves into 1D strings. And there is one more major issue the sources detail before the model completely stalls: the simplistic scalar mass defect.
To understand this flaw, we really need to define mass defect first. It is the widely observed phenomenon where particles actually lose a tiny measurable fraction of their mass when they bind together.
Right.
When a proton and a neutron bind to form an atomic nucleus, the mass of the resulting nucleus is slightly less than the sum of the individual proton and neutron.
That missing mass is what gets released as immense binding energy.
Exactly. Vrbovsky attempted to account for this mass defect, but he treated it as a simple scalar. He just treated it as a flat, dimensionless number subtracted from the total virtual mass.
But what is fundamentally wrong with that? We all know E equals mc squared. Mass converts into energy, so you just subtract a number. Why does that break the framework?
The problem is internal consistency. Vrbovsky's own foundational postulate, the entire basis of his framework, states that mass is not a scalar number. Mass is an electrodynamic field.
Oh, I see.
And fields are not scalar numbers, they are vectors. They possess directionality and spatial orientation. If you bring two massive magnetic fields close together in three-dimensional space, how they interact, how they repel or attract, depends entirely on their orientation and angle of approach.
And a simple scalar number completely fails to account for the complex directional reality of interacting vector fields in 3D space.
Exactly. So by treating mass defect as just a simple arithmetic subtraction, he was basically ignoring his own revolutionary premise that mass is a localized field.
The classical model was truly at a breaking point. It provided an incredible intuition that inertia is an electromagnetic, self-inductive back reaction. But the 19th century mathematics just couldn't support the 21st century physics required to make it work at extreme limits.
Which brings us to the pivotal transition in the source material. Act 3, the 20-year debate and Vrbovsky-Banić's quantum intervention.
I want you listening to really imagine the timeline of the struggle here. You have a 20-year intellectual debate spanning from Bački Petrovac in Serbia, across the Atlantic Ocean, to Brighton, Michigan.
That's a long time to be stuck on a paradox.
Yeah. For nearly 2 decades, this beautiful theory of electrodynamic mass was essentially stuck in theoretical purgatory. It was a brilliant idea trapped in paradoxes. Vrbovsky-Banić steps into this arena to rescue Vrbovsky's foundational intuition.
He had to do some heavy lifting.
He did. To save the theory, Banić has to ruthlessly rip the framework out of the smooth, continuous 19th century classical world and plunge it deep into the chaotic, discrete mathematics of nonlinear quantum field theory.
Banić diagnosed the core issue perfectly. He realized that the problem wasn't Vrbovsky's foundational idea of electrodynamic inertia.
What was it then?
The problem was the physical nature of the medium Vrbovsky was using. Vrbovsky was treating the vacuum of space and the magnetic self-energy cloud itself as classical, smooth, continuous fields, like a perfect, unbroken fluid.
Right.
Banić fundamentally alters this by introducing postulate the sixth, the quantum statistical foundation of mass.
Let's ground this. What does a quantum statistical foundation mean for the actual structure of the particle?
Banić argued that we must look at the localized electromagnetic self-energy cloud around a moving charge through the lens of quantum electrodynamics, or QED.
Okay.
In QED, we know that electromagnetic fields are not smooth, continuous waves. They're actually composed of discrete, quantized particles called virtual photons.
These are the little packets of light that constantly pop in and out of existence in the vacuum to mediate the electromagnetic force between charges.
Exactly. They are the fundamental carriers of the force. And crucially for Banić's theory, photons possess an integer quantum spin of 1.
Which means?
In quantum mechanics, any particle with an integer spin is classified as a boson. This is a vital distinction. Fermions, particles like quarks and electrons that make up solid matter, they have half-integer spins, and the Pauli exclusion principle dictates that they cannot occupy the same quantum state at the same time.
They stack up, they take up space.
Right. But bosons, like these virtual photons, are highly gregarious. They love to clump together. Infinite numbers of bosons can occupy the exact same quantum state at the exact same time.
So Banić is shifting the paradigm. He is saying, let's stop modeling the mass of a particle as a smooth, classical magnetic sphere. Let's model that virtual mass shell as a dense, swarming, highly compressed gas of virtual bosons governed entirely by quantum statistics, specifically the Bose-Einstein distribution.
And here is where we apply the pressure. What happens when you take a swarming gas of bosons and you severely compress it? Banić showed mathematically that when these virtual photons are compressed into the incredibly tight subquantum radius of a fundamental particle's boundary, their spatial density skyrockets.
Because they're packed into such a tiny space.
Right. They are packed in so tightly, localized in such a microscopic volume that they cross a critical quantum threshold.
Here's where it gets really interesting. Because when they cross that extreme density threshold, the physics completely changes. They undergo a phase transition.
Yes. The swarming gas of individual virtual photons collapses into a single, coherent, macroscopic quantum state. It becomes a Bose-Einstein condensate, commonly referred to as a BEC.
I want to pause and make sure we emphasize the magnitude of this concept, because this is the paradigm shift of the entire deep dive.
It really is.
Banić is proposing that the physical rest mass of a fundamental particle, the actual physical property that gives a quark or an electron its heft, its inertia, is mathematically and physically defined exactly as the ground state energy of this trapped Bose-Einstein condensate of virtual photons.
That is the immense conceptual leap. Mass is no longer a static label. Mass is a trapped quantum superfluid. It is a dynamic, condensed state of virtual light.
Mind-blowing.
And Banić didn't just theorize this as a philosophical model. He rigorously calibrated it with known physics. He took the quantum statistical equation for the energy of this trapped BEC, and he equated it to the known, experimentally verified virtual rest mass of a proton.
Working backwards.
By running that calculation in reverse, he was able to extract a specific, localized vacuum temperature required to maintain this sub-quantum boundary state.
The outline highlights a very specific calibration point here. What was the vacuum temperature he calculated for this BEC state?
According to the specific derivation in the sources, he calibrated this quantum boundary temperature, T sub-vac, at exactly 39.5 GeV, or giga-electron volts.
39.5 JV. To provide context for you listening, that is an extreme energy scale. That is an astonishing, staggering amount of energy density localized in a microscopic subatomic space.
It definitively proves we are no longer dealing with simple classical magnetism.
No, we are dealing with intense, high-energy, quantum hydrodynamic forces shaping the fabric of the particle.
And by establishing this new reality that the mass shell is fundamentally a Bose-Einstein condensate operating at 39.5, Banić was finally perfectly positioned to go back and methodically fix every single one of Vrbovsky's universe-breaking classical paradoxes.
Which leads us into Act 4, resolving the paradoxes through QED and thermodynamics.
Let's get into it.
Okay, let's tackle the biggest monster first, the one that broke Einstein's causality. The internal permeability paradox, the faster-than-light problem.
Right.
Remember, listener, Vrbovsky's classical model mathematically required the inside of the particle to have a magnetic permeability of less than 1 U sub R2 is less than 1. So the magnetic pressure could actually push inward and compress it.
But classically, a permeability below 1 meant the phase velocity of light inside the particle exceeded c.
Right, so how did introducing a BEC fix this physical impossibility?
We have to look at the defining physical characteristics of a Bose-Einstein condensate. What is the most famous observable property of a BEC, or any superconductor for that matter, when it is exposed to an external magnetic field?
It aggressively expels the magnetic field. It doesn't let the field lines penetrate it.
Exactly. It's a phenomenon called the Meissner effect. If you place a magnet over a superconductor in a lab, the superconductor generates surface currents that perfectly oppose the magnet, expelling the field lines and causing the magnet to levitate.
Like those floating magnet demonstrations.
Yeah. Banić realized that this exact mechanism applies at the subatomic level. The subatomic BEC that forms the mass shell actively, forcefully expels its own self-generated magnetic field lines from its interior volume. This is defined in the framework as the vacuum Meissner effect.
So the magnetic field generated by the moving charge is trying its hardest to push inward to compress the particle. But the internal BEC is a perfect diamagnet.
Yeah.
It is actively fighting back, expelling the field lines, refusing to let them easily penetrate.
Right, and this physical dynamic expulsion is what actively drives the relative permeability, mu sub R2 below 1. In Vrbovsky's classical model, mu sub R2 less than 1 was just a naked mathematical requirement that caused a paradox because there was no physical reason for it to happen. In Banić's quantum model, mu sub R2 less than 1 is the natural, unavoidable physical consequence of a quantum hydrodynamic superfluid exhibiting the Meissner effect. It provides the physical why.
I understand how the Meissner effect physically justifies the permeability dropping below 1. But I have to push back again because we haven't actually solved the core issue.
You're thinking about the math.
Yes. Even if the Meissner effect beautifully explains why the permeability drops below 1 physically, doesn't that still leave us with the exact same mathematical paradox? If mu sub R2 is physically forced below 1, doesn't the classical equation V subphase equals C over the square root of epsilon sub R2 times mu sub R2 still inevitably result in a phase velocity faster than light? If you shrink the denominator, the result still gets bigger than C. Doesn't that still break causality, regardless of whether a BEC is causing it or not?
This raises an important question, and it is the exact mathematical hurdle Banić had to clear to save the theory. And his answer relies on introducing an incredibly powerful tool from advanced physics, the nonlinear Euler-Heisenberg effective Lagrangian for quantum electrodynamics.
Okay, that is quite the title. Let's demystify the Euler-Heisenberg Lagrangian. What is it actually doing in this context?
Let's break it down conceptually. Basically, classical physics assumes the vacuum of space is perfectly linear and empty. It assumes light waves just pass through it without changing the medium itself.
Like light going through a clear window.
Right. But the Euler-Heisenberg-Lagrangian acknowledges that at this extreme subquantum scale, dealing with energies around 39.5 GeV, the electromagnetic fields are so unimaginably intense that they literally polarize the vacuum itself.
Polarize the vacuum.
Yes, the vacuum isn't empty. It is a roiling sea bubbling with virtual electron-positron pairs. The intense field strength of the particle interacts with these virtual pairs, aligning them, and essentially turns the interior volume of the particle into a highly nonlinear medium.
Okay, so the extreme energy turns the vacuum from a clear window into a warped, nonlinear medium. What does a nonlinear medium actually do to the speed of light propagating through it?
This nonlinear QED vacuum polarization dynamically constantly adjusts the internal refractive index of the space. And here is the crucial physics distinction that saves causality. In a nonlinear medium, you absolutely must distinguish between the phase velocity and the group velocity, or signal velocity.
What's the difference?
Phase velocity is just the speed of the individual ripples within a wave. Group or signal velocity is the actual speed at which the overall wave packet, the physical energy or the information, actually travels from point A to point B.
Ah, so it's like watching a caterpillar move. The little ripples on the caterpillar's back might propagate forward very quickly, but the actual body of the caterpillar, the physical mass, is moving much slower.
That's a really great visualization. In Banić's application of the Euler-Heisenberg-Lagrangian, while the mathematical phase velocity appears superluminal due to the m sub r2, less than 1 condition forced by the Meissner effect, the nonlinear QED interactions act as a strict speed limit on the actual wave packet.
So the physical energy can't break the limit.
Exactly. Banić proved rigorously that the physical group and signal velocities remain strictly subliminal and causal. The signal velocity is always mathematically forced to be less than or equal to the speed of light. Information does not and cannot travel faster than light in this nonlinear medium. Einstein's relativity and cosmic causality are completely saved.
That is just brilliant. He used the inherent quantum weirdness of the vacuum itself to decouple the mathematical phase velocity from the physical signal velocity, allowing the particle to compress and possess mass without breaking the universe's ultimate speed limit.
It's an elegant save.
Okay, so that is one massive paradox down. What about the geometry problem? The asymmetric equatorial boundary collapse. How did Banić prevent the particle from crushing into a useless 1D string at the equator when it is subjected to the toroidal magnetic pressure near the speed of light?
To solve the geometric collapse, Banić focused intensely on the actual boundary interface of this subatomic BEC. Because the mass shell is a superfluid, its boundary isn't a rigid classical wall. It acts as what is known in thermodynamics as a Ginzburg-Landau phase interface.
Ginzburg-Landau, okay.
The sources specifically note that Banić utilized a Ginzburg-Landau boundary parameter denoted as kappa equal to 1 over the square root of 2.
Let's unpack the Ginzburg-Landau interface and this kappa parameter. How does a fluid boundary resist the crushing asymmetric magnetic pressure that destroyed the rigid classical sphere?
It resists through highly dynamic thermodynamic venting. As the external magnetic field pushes in incredibly hard on the equator of the particle at relativistic speeds, the BEC boundary doesn't just statically crumble or flatten.
Because it's fluid.
Right, because it is a fluid interface at that critical kappa equals 1 over square root of 2 threshold, it undergoes a thermodynamic phenomenon called phase slip cascades.
Phase slip cascades.
Imagine the magnetic pressure building up mercilessly at the equator. In a classical sphere, the wall just breaks. But in a Ginzburg-Landau interface, the pressure builds until it reaches a critical breaking point, and instead of the entire geometric structure collapsing, the localized boundary essentially slips its quantum phase. It momentarily drops its order parameter to 0 to relieve the localized pressure.
It breaches intentionally. And when it phase slips, what is it actually doing? How does that relieve the pressure?
During a phase slip, the boundary violently ejects localized packets of energy back into the surrounding vacuum. Specifically, it ejects Bogoliubov phonons.
Phonons, like sound.
Well, in standard condensed matter physics, phonons are usually quanta of sound or vibration. But in the extreme context of this subatomic BEC, these Bogoliubov phonons manifest as ejected virtual photons.
It's acting exactly like a mechanical pressure relief valve on an overpressurized steam engine, but it's operating continuously on a subquantum electrodynamic level.
Precisely. Every single time, the intense asymmetric magnetic pressure threatens to collapse the 3D spherical geometry into a 1D string at the equator, the Ginzburg-Landau boundary actively, dynamically vents energy outward through these rapid phase slips.
Just constantly bleeding off the pressure.
Yes. This constant, furious cycle of slipping and venting Bogoliubov phonons continuously pushes back against the equatorial pressure. This incredibly dynamic interface actively stabilizes the 3D spatial structure. It prevents the 1D collapse and ensures the particle remains a functional, three-dimensional entity even at extreme relativistic speeds.
Vrbovsky's classical sphere was too rigid, so it broke. Banić's quantum BEC boundary is dynamic, fluid, self-regulating, and literally vents pressure to survive. That is structurally beautiful.
It's nature finding a way to balance extreme forces.
Okay, we have causality saved, we have 3D geometry saved. That brings us to the final classical flaw we need to address from the outline. The simplistic scalar mass defect.
Right, the mass loss.
Remember, listener, Vrbovsky just subtracted a flat scalar number to account for the mass lost when particles bind together, completely ignoring the fact that magnetic fields have 3D directionality. How did Banić solve this and account for vector physics?
Banić solved this by deeply analyzing the physical reality of overlapping electrostatic and magnetic fields. When two nucleons, for example, a proton and a neutron, bind together to form an atomic nucleus, they are brought incredibly close together in space.
They don't just sit next to each other.
No, their individual, co-moving electromagnetic fields physically overlap and interact in the shared vacuum space between them.
And because these magnetic fields are fundamentally waves, when they overlap in the same space, they must interfere with each other.
Exactly. Depending on their alignment, they spatially superimpose. In a stable bound state, these overlapping fields destructively interfere in the vacuum. This destructive interference physically reduces the total net magnetic field energy in that local space between the particles.
Let me make sure I'm piecing this mechanism together correctly. The localized magnetic fields were the exact mechanism providing the inward pressure to compress the particles and give them their high mass.
Yes.
If those fields destructively interfere and physically weaken each other, then that inward magnetic pressure on the particle's boundaries must relax.
Yes, exactly. Because the Krushen inward magnetic pressure is reduced by the destructive interference, the subatomic BEC boundary of the individual particles is allowed to slightly physically expand outward.
And what was the absolute core relationship we learned from Vrbovsky's virtual mass equation back in Act 1? Mass is inversely proportional to radius.
If the inward pressure relaxes, the radius physically expands.
And if the radius expands, the mass mathematically drops.
This physical volumetric expansion of the particle's radius literally is the mass defect. The loss of mass when fundamental particles bind isn't some abstract magical conversion of matter to energy written on a chalkboard. It is the literal physical expansion of the particle's thermodynamic boundary due to destructive vector field interference relaxing the inward magnetic pressure.
That is a staggering realization. It provides a completely physical, mechanical, geometric explanation for a phenomenon that is usually just written as E equals mc squared and left fundamentally unexplained.
It grounds it in physical reality.
And because he is explicitly dealing with overlapping directional vector fields to cause this expansion, Banić inherently fixes the math too, right? He can't use a simple scalar number anymore.
No, a scalar is entirely insufficient. Because these fields are directional vectors, how much they destructively interfere, and therefore how much the radius expands and how much mass is lost, depends entirely on the exact angle and orientation at which the particles bind.
So it's directional.
Banić proved mathematically that bound system inertia is intrinsically direction-dependent. To represent this mathematically, he replaced Vrbovsky's simplistic scalar number with a highly precise, symmetric rank 2 mass defect tensor, denoted mathematically as M sub ij.
Let's explain that tensor to the listener.
Yeah.
A rank 2 tensor means it's a mathematical matrix that accounts for different magnitudes across different spatial dimensions. So what Banić is proving is that a bound atomic nucleus might actually have slightly different inertial resistance. It might literally be harder to push, depending on which specific three-dimensional direction you apply the force from.
Exactly. It's called anisotropic inertia. The mass defect, and therefore the total mass of the bound system, varies slightly based on the orientation of the overlapping fields along the x, y, and z axes.
Wow.
It is a completely radical, deeply counterintuitive, yet mathematically and physically sound departure from the assumptions of classical Newtonian mechanics.
Okay, let's take a deep breath and look at the absolute paradigm shift we've just journeyed through over this hour. For you listening, just take a moment to think about how this entirely transforms our fundamental view of the universe.
It's a lot to take in.
It really is. Over a 20-year transcontinental debate, we moved from treating mass as an unexplained, axiomatic constant, a static label slapped on an object, to rigorously proving it is a localized, highly dynamic, Bose-Einstein condensate of virtual photons, operating at 39.5 GeV, trapped in a nonlinear, superfluid vacuum.
The old models just don't hold up.
The empty void of space you see when you look up at the night sky does not exist. The vacuum is not nothing. It is a dense, contiguous, incredibly active, quantum superfluid medium. Every single time you move your arm, every time a leaf falls, every time a massive planet orbits a star, they're actively interacting with, polarizing, and pushing through this immense superfluid medium.
The physical resistance you feel in everyday life is the universe actively recalibrating its electromagnetic fields at the quantum level.
It changes the entire foundation of how we approach the physical sciences. It means basic kinematics and physics are not just exercises in geometry. They are fundamentally exercises in extreme quantum hydrodynamics and nonlinear electrodynamics.
But as we promised at the start, we want to end this deep dive with a final provocative thought, an extrapolation.
Oh, right. The black hole implication.
Yes. If we take everything we have just discussed from the source material, the nonlinear vacuum polarization, the superfluidity, the Meissner effect, the purely electrodynamic nature of mass, and we point this new framework at one of the biggest, most terrifying mysteries in the cosmos, what happens? I'm talking about the centers of black holes.
This is where the implications of the redefined mass framework get truly conceptually mind-bending. In standard general relativity, the math dictates that if enough mass collapses under the weight of its own gravity, it forms a black hole.
Right.
And if you follow the classical math to its conclusion, it says the matter crushes down infinitely into a zero-volume point called a singularity, a microscopic point of literal infinite density and infinite gravity.
Which physicists famously despise, because anytime an infinity pops up in a physics equation, it almost universally means your math is broken, incomplete, or missing a fundamental limiting factor.
Right. Infinities in nature are usually mathematical artifacts of bad assumptions.
So let's reevaluate gravity through the lens of the framework we just built. If mass is explicitly an electrodynamic field state, then gravity cannot simply be the geometric curving of an empty space-time void as Einstein modeled it.
Right, because the void isn't empty.
Exactly. Gravity must fundamentally be an electrodynamic force mediated by this exact same background superfluid vacuum, and if it relies on the vacuum to mediate the force, it is subject to the rigorous thermodynamic, dielectric, and polarization limits of quantum electrodynamics.
So gravity have physical quantum limits. It cannot just scale to infinity unchecked.
Exactly. The source materials dictate that as matter falls into a black hole and the gravitational pressure increases immensely, the system relies entirely on polarizing the surrounding vacuum to transmit that ever-increasing attractive gravitational force. But there is a hard physical limit to polarization. Before the infalling matter can ever crush down into a zero-volume point, a singularity, the absolutely intense, mind-boggling gravitational potential completely saturates the vacuum polarization susceptibility.
Wait, meaning the vacuum itself is completely maxed out.
Yeah.
Like a physical sponge that has absorbed so much water, it physically cannot hold a single drop more, no matter how much water you pour on it.
Precisely. Once the surrounding subquantum vacuum is fully 100% polarized by the gravitational field, the medium physically cannot transmit any more attractive force. It hits an absolute unbreakable quantum electrodynamic ceiling.
So what happens to the collapse?
Because the transmission of the attractive force is physically cut off by the saturated medium, the gravitational collapse must physically halt. It stops collapsing at a finite non-zero radius.
So, the math dictates that singularities might not actually exist. At the absolute center of a black hole, there isn't an impossible infinite point. There is a highly compressed, incredibly dense but physically finite 3D structure resting at the absolute thermodynamic limit of the vacuum's ability to polarize.
That is exactly the profound cosmological reality that the redefined mass framework predicts. The vacuum saves the universe from infinite collapse.
That changes absolutely everything about how we understand cosmology and astrophysics. If black holes aren't singularities, if gravity is an electrodynamic force running through a saturated superfluid vacuum, it means we have to reevaluate the entire large-scale structure, origin, and fate of the universe.
It opens up so many new questions.
And listener, if your mind is spinning right now, if you are struggling to comprehend a universe completely filled with superfluid light, you are exactly where you need to be. Because this seamlessly transitions into the incredible topics we're going to tackle in the next deep dive.
We have a lot more ground to cover.
We really do. In Episode 2, we are going to seize on this immense conceptual momentum. We are going to explore how this superfluid vacuum model solves the long-standing entropy paradox, how it finally explains the baffling mystery of coronal heating in stars, and how it demystifies the profound, haunting puzzle of the fine structure constant. We're going to look at all of it through the lens of this newly defined universe. But until then, I want you to remember our opening hook. The next time someone tells you something in science is perfectly clean, binary, or axiomatic, just remember that their classical framework might be broken. There is always a deeper, more turbulent, and infinitely more fascinating quantum reality waiting just beneath the surface.